This is Math 30-1, and we're looking at Chapter 4, where we're combining functions together. And in 4.2, we're going to start looking at combining functions algebraically. So when we say combining functions, we're thinking about performing those four operations of addition, subtraction, multiplication, and division. In our previous lesson, what we did was we looked at performing these operations on functions where we were given the two functions graphically rather than in terms of equations. And so that was hopefully not too bad. One idea I do want to briefly review as we start this lesson is kind of at the end of that introductory part, we looked at domains of the functions when we're going to combine them together. And what we observed is that when I have two functions, so here I have f of x and g of x. G of x is this reddish pink graph, and f of x is this black dotted line kind of graph. If I'm going to combine the functions together, no matter what the operation is, I need to limit the domain of that combination of the two functions to where the domains of these two original functions overlap. So if I thought in terms of a number line, this first graph, we're going from -4 up to +5, if I was to think of that on a number line, although I didn't draw the whole number line. And then for this g of x function, it had a left end at -5 and a right end at +3. So when we come to looking at combining the two functions together, we have to take the intersection or the overlap of these two domains. So we're only going to look at this section in here, which goes from -4 up to +3. And so that's the domain that we wrote here for g minus f of x. And again, you'll remember this notation just means I'm taking the g of x function and I'm subtracting the f of x function from it. Okay, so this notation means this. There's nothing algebraic about it. This x is not distributed into brackets because it's not being multiplied. This is function notation for the subtraction of two functions. Okay, so this is defined to mean this. There's no algebra in it. Okay, the one exception, well, not exception, but the one additional restriction we needed to consider was when we were dividing the two functions. So if we're dividing two functions, we also need to consider what makes this denominator function 0. So that's what we looked at here, and we saw this denominator function was 0 all the way from -4 up to -2. And so we said, well, if I do g of x divided by f of x, there'll be no function in this section because I'd be dividing by 0. But then starting from this point, I get some negative y values, some negative function values for f of x. And so my division of the two functions would be defined all the way up to this point. And so our domain, when we were dividing the two functions, would have been here from -2 up to +3, and that's the domain that we wrote there. So that's just a quick review of how domains are affected when we are combining two functions together. With that in mind, I would like you to take some time here to do this warm-up question. So a couple warm-up questions actually. We're going to look at these two polynomial functions. And first of all, we'll state the domains and ranges of each of them. Now domains, typically we can find domains algebraically. Ranges, sometimes we can, sometimes we can't. Feel free to use your calculator to find these ranges. That would be all right. So then we're going to subtract the two functions, and then what is the simplified equation? And we'll also look at what's the new domain and range for h of x, where h of x is the subtraction of the two functions. So that'll be the first set of questions. The next set of questions, you're going to look at dividing the two functions. And again, you'll look for a simplified equation, and then you'll state the domain and range. So pause the video at this point and work through these 5 questions, please. Well, hopefully you finished. Both of these functions are polynomials, so they will have domains that are all real numbers. They're both quadratics, and so their graphs are parabolas. A value is positive, so they open up. So they have minimum values. The first one has a minimum value of -4, and the second has a minimum value of -9. As you look at the simplified equations, when we subtract, what I did was I wrote f of x over g of x, and then I lined up the like terms just to make life easier for myself, and then subtracted. The x squareds cancel out. -2x minus nothing is -2x. -3 minus a -9 gave me a +6. You could do this all in one line, but I thought it would be easier on my head just to do it by aligning the terms like this. Then as we look at the domain and range, again, this is a polynomial. And so the domain is all real numbers. It's linear with a negative slope, which means its range is also all real numbers. So notice that the range of this combined function is not limited by the range of the original function. That's important. Domains can be restricted. In this case, they're not, but they could be, as we saw with our graphical examples that we initially reviewed. Ranges, initial range does not affect the final range. We can get whatever y values turn up. All right. Then as we look at number 4, when we're dividing the two functions, I've written f of x over g of x, and I factored to find, hey, there is a common factor. So this x minus 3 and that x minus 3 cancel out, giving me a simplified equation of just x plus 1 over x plus 3. And I wrote down the restrictions right away, and the factored form helped me find those restrictions. So again, I looked what values for x make the denominator 0, and I discover it's positive -3, which is also answering my question about the domain. X can't equal positive or -3. The range. Well, here we could look at the graph, but we may miss a point. So keep in mind that when we have a term left in the denominator, as we do here, no common factor, which means this will tell me where there's a vertical asymptote. And so I will have a vertical asymptote when x is -3. But here, this common factor is giving me a point of discontinuity. And so I'll have a hole in my graph, which means I'll be missing a y value also. So here is my range. Y can't equal 2/3, and it can't equal 1. And where these are coming from again is I have a hole and I have a horizontal asymptote. So let's talk about the hole first of all. So just to review those ideas that we learned in the previous chapter, chapter 2, here my x value can't equal a +3. That's where the hole came from. So if I plugged that +3 into here and said, well, what's k of 3, ignoring these restrictions, I'd get 3 plus 1 over 3 plus 3, which gives me 4 over 6, and that reduces to this 2/3. So that's where I'm getting that gap in my range. And then as I look at this and I see my leading coefficient is 1, they are the same degree, so I have a horizontal asymptote at y equals 1. So that's also a value that's excluded from the range for this function. If you need to, you can pause and review these ideas, but let's look ahead to some more examples. Well, before we get to the examples, let me summarize. When we have two functions, added, subtracted, multiplied, the domain for the new function is the set of values that are common to the domains of both f of x and g of x. It's the overlap, it's the intersection of those two domains. Now notice I left out division. We'll talk about that in a moment. In our next bullet, in fact, when two functions are divided, like f of x divided by g of x, the domain of the new function includes all the original restrictions on f and g. So same things we put in bullet 1. It has to be where these two functions overlap, but we also have to exclude values where we would get g of x, our denominator function, equal to 0. So again, we can get new restrictions as we did in the last example on the previous page. And the third bullet here, we want to use the graph and the domain of the combined functions to determine the range. So graphs will always be useful to look at. We didn't actually look at a graph in our last example because we understood enough from the work that we did back in chapter 2. Let's look at another similar example. Now we have f of x and g of x. These two functions are rational functions now. And let me have you just pause to review again and determine what are the domain and range of these two functions. Pause the video now. There I have my domains for the functions, and they both have the same domain. Neither is defined when x is equal to positive 3. I factored the f of x function to make it a little bit easier for me to see that restriction. And then for the ranges, the first one, we get a range that looks like this, negative infinity up to 0, and then from 6 to positive infinity, including the 0 and including the 6. To get this range, a graph is helpful. And here's what the graph looks like when I stick it into Desmos. You could do it on your graphing calculator, and then you would want to find what's the maximum value here. So again, use that second trace to bring up the calculate menu, and you'd calculate a maximum doing left bound, right bound, and guess. If you have a TI 83 or 84. If you have an Inspire, again, you would analyze the graph by finding a maximum, and you'd click and drag across that maximum. Same thing for the minimum here. So we can see the y value max is a 0, the y value minimum up here is a 6. So that's how we can get the range for that first function. Second function is a little bit more straightforward because I can see numerator and denominator are the same degree. And so I know I'll have a horizontal asymptote, and I'll do the leading coefficients, the 2 over the 1, which gives me a 2. And again, we could always verify that by graphing. So let's find a simplified equation when we add these two functions together. And then we're also going to state the domain and range. So here I have the two functions. I took my f of x function and I took it in factored form for the denominator because that makes it a little bit easier for me to recognize, oh, to get a common denominator, I need to multiply g of x by 2 over 2. Again, remember this notation just means I'm taking the f of x function plus the g of x function. Well, then we can combine them together over that common denominator. You could expand the denominator if you like. I typically leave it in factored form for two reasons. One reason would be, well, maybe there's a common factor I could cancel out. Another reason would be, the more operations I do, the more likely I am to make a mistake. So this just limits the possibility of making mistakes. All right, go away. Now let's look at the domain and range. So as I look at my new function combined together, I can see that I still just have that same restriction as I had previously, that x cannot equal 3. So domain, pretty straightforward. Same as my original domains for those two functions. Range, again, I want to look at a graph. My numerator is higher degree than denominator, and it's higher by 1, which means there's a slant asymptote, which we never figured out how to do, but that's fine. So again, I'm going to look at my graph and then find the maximum value here and the minimum value there. Again, I'm looking at the y values. So this is what my range would look like. Negative infinity up to negative 0.4, and I'm just doing a rounded value, square bracket to include this, and then 9.6 to positive infinity. Notice here I did a rounded bracket. I won't be super picky here if you did a square bracket. The reason I did rounded is because this doesn't actually reach 9.6. So a better answer is to do the rounded bracket where I round this to 9.6. If this had been 9.52 and I'd rounded down to 9.5, here I would write 9.5 with the square bracket. Okay, that's a pretty picky detail that I won't be super picky about when it comes to marking. So I'll be a little bit flexible with that. But the more precise you can be, the better, because that's going to help you going forward with whatever you're going to use this math for in the future. All right, next question. We are going to do the division of the two functions and again state the domain and range. So this time, notice I chose not to write f of x over g of x. And I chose this because my two functions are rational functions. If I do a rational function over a rational function, it's just a pain, like a fraction over a fraction. Not very pleasant to work with. But if I write it like this, then it's a little bit easier for me, takes me a step further, and then I can recognize, oh yeah, this g of x function, I can take the reciprocal and multiply. And when I do that, I can look for common factors again. So here, notice here, this 2 and this 2 I couldn't cancel out because I was dividing. But here, this x minus 3 and that x minus 3, I can cancel out because they're common factors with multiplication. And then we'll simplify to just get x over 4. And you'll see that I already wrote the restrictions on my function. So let's take a minute, go back and look at those restrictions. Pause the video if you need to copy some stuff down, but I'll just keep going here. So let me go with black. So what restrictions do I have? Well, oh, I also didn't show another thing I canceled out. This x cancels with one of those x's. So that's why I just have an x in the numerator and I don't have any variables in the denominator, just this 2 times 2. All right, so everything canceled out. But at this point, I did have this x minus 3 in the denominator, so that tells me that x can't equal 3. And here, I had that x as a factor in the denominator, which tells me x can't equal 0. So when we are dividing two rational functions, we need to look at this point and say, what are the restrictions here before I flip this? In this case, I don't have any restrictions different from the end, but this is a good point to look for restrictions. X can't equal 3, x can't equal 3. Then when I flip this second rational expression, I look to see, are there new values in the denominator? Okay. Another way I could have done it is I could have said, well, here I'm dividing. I can't divide by 0, so that tells me this x can't equal 0 at this point. That's a little bit trickier for some people, and so if we just look at this point, it will give us that restriction. And most people find more success when they do it at this point. Recognizing it here, great if you can recognize it. So that gives us our domain as well. And so our range, again, we'll need to look at the function. Here, this is going to look like a line, but there are two x values that don't exist. So there are going to be two y values that don't exist as well. Again, where do those y values come from? Well, if x is equal to 0, then y is equal to 0 over 4, which is 0. That is a 4. Or if x is equal to 3, y is equal to x over 4. Oh, there we go. So I found the y coordinates that go with these two x values if they had existed. But since they don't exist, these two y values don't exist. There we have the domain and the range. And again, I wrote just an abbreviated domain range. I didn't use set builder notation. and I didn't use interval notation. If you're not told, then we have some flexibility for how we're going to write those domains and ranges. Next page. Now we'll look at rational functions. I should say radical functions, and what happens if we're going to combine these together. So once again, I'm going to have you pause and state just the domains of these two functions, please. Pretty straightforward for that first function. We just have an x as a radicand, so x has to be greater than or equal to 0. For g of x, a little more effort is required. Again, we look at this radicand and we say that radicand has to be greater than or equal to 0, and then we solve that. So I added the x to the right-hand side, got 4 is greater than or equal to x. If I flip everything around, I get x is less than or equal to 4. These two statements are identical. Then for number 10, we're going to look at a simplified equation for the product of these two functions. So there are the two functions, multiplying them together. And remember, when I have two square roots being multiplied, I can just multiply the two radicands together. So this x times 4 minus x gives me the 4x minus x squared. So again, I just took this x times that 4 minus x, put it under the square root sign. So there we have the product of the two functions. Now let's think about the domain. So first of all, what I did here was I drew some number lines just to help us think it through. For the f of x function, my domain looked like this. It was from 0 to infinity, including the 0. My g of x function was from 4 to negative infinity, and it looked like that. And so you'll remember from the beginning of today's lesson, or the end of the previous lesson, that we observed if we're going to be combining these two functions together, the domain of the combination has to be where these two intersect or where they overlap. So it's going to come up to this point, and it's going to come up to this point, and then every point in between is where the two domains overlap with each other. So here I've drawn that out for the product of f times g. So from that, I can say that my x value is going to be greater than or equal to 0, less than or equal to 4. And when we write a compound inequality like this, and we're doing values in between some endpoints, we always do the smallest on the left, biggest on the right, kind of similar to when we did interval notation, and where with interval notation, we'd put 0 on the left, and then the 4 on the right, and then we'd use the bracket to tell us we're including these endpoints. There's number 10. Let's look ahead to numbers 11 and 12. Here I've called them examples, but I want you to try these first. So we're going to do something a little bit different here. So now we're given this function p of x, and we want to write explicit equations for f of x and g of x so that p of x is the product of these two functions. So p of x we know. Use your imagination. What might f of x be? What might g of x be? So that when you multiply them together, you end up with this function. Similar idea for number 12. Now we're going to divide two functions to end up with this q of x function. What might these two functions be so that when you divide them, you end up with this as a simplified expression? So pause the video here and do questions 11 and 12, please. Well, here's one answer you may have gotten. I chose f of x to be x plus 3, g of x to be x minus 3. So that if I multiply them together, then the result that I get is that p of x function, which is x squared minus 9. Is this the only solution? Well, no, because we could have switched these two around. That would be another solution. Are those two the only solutions? Well, no. There's another one where we could say, well, suppose f of x equals 1. then what would g of x have to equal? Well, it could be x squared minus 9. Does this work? Yes. Is it true? Yes. Does it show me that you understand? Not so clearly as these two do. So remember, when you're writing a test or a quiz, your goal is to clearly communicate the extent of your understanding. And this will show more understanding than this does. So I'd recommend you not do this one on a test or a quiz. Do something more like this on a test or a quiz because it shows better understanding. How about for question number 12? Well, here's my q of x function. And so kind of similar to what we did in chapter 2, what I could do to get something to simplify down to this is I could actually multiply it and divide it by the same expression. So suppose I chose x plus 1 to multiply and x plus 1 to divide. Would this simplify down to x minus 1? Yes, it would. So notice in this question, I wasn't given any restrictions on the variable, so I have a fair bit of freedom in terms of what I'm going to pick. So does that mean that f of x is x plus 1 and g of x is x plus 1? Well, not quite. Because remember, well, let me first expand this out. I would get, in the numerator, x squared minus 1. And in the denominator, I will have x plus 1. And what we wanted is for this to equal the f of x function divided by the g of x function. So is g of x x plus 1? Yes, it is. Is f of x x plus 1? No. F of x is x squared minus 1. This entire function has to be my f of x function because of how this is written here. My entire numerator is that f of x function. Is this the only solution? No. In this case, there are an infinite number of solutions. And so all kinds of possibilities you may have come up with as answers for this question number 12. But that takes us to the end of this lesson. Given their equations, can you add, subtract, multiply, and divide two functions? And I hope the answer is yes. And there will be practice questions here for you just to test that out. Is that true for you? And then, given the equation of two functions, can I state the domains and ranges of the function that results from adding, subtracting, multiplying, dividing? So those are our measures of success from today's lesson. And here are some questions for you to practice just to reinforce your understanding of those ideas. That'll be the end for this lesson, and I'll see you again on a future lesson.